Okay.
Hi, we're going to do a little review of Lab 6. We just did this a couple weeks ago, so I hope it's fresh in your mind, and you should take your sheets out and review what you wrote. There were some very salient, good questions there, okay? What we did in lab was we took a compound called chlorobutane, and we chlorinated it using sulfuryl chloride and a compound called AIBN, and I'm going to talk about that in a second. And our goal was to produce these 4 compounds, okay, plus SO2 plus HCl, okay? As I told you in class, this was a free radical reaction. AIBN is a free radical initiator, okay? Sulfuryl chloride is analogous to Cl2, which is your chlorine source. Okay, and this was your substrate. The goal of the lab was to study the effect of this chlorine on free radical substitution at these various locations. Okay? We use sulfuryl chloride instead of chlorine gas because it's a liquid and it's easy to measure out, although it is a tear gas or a lacrimator. And I told you, think of onions, not of canisters of tear gas being thrown. It's like a relatively mild tear gas. AIBN is a compound that spontaneously produces free radicals. And our goal was, in particular, to get these 2 compounds, both of which are secondary. Okay? We were going to figure out how reactive the hydrogens were based on how much product we got. In other words, if I got mostly this product, that would be an indication that these hydrogens were the most reactive. So we were correlating the amount of product with the corresponding hydrogens, the reactivity of the corresponding hydrogens. Okay, mechanistically, I'm going to give a little bit of the mechanism. What's going on? AIBN is this compound. I may have to do this little review in 2 shots, we'll see. But one of them is going to come out today. One shot is going to come out today. AIBN is this very complicated compound called azo-bis isobutyronitrile. So we always call it AIBN. When you take AIBN and you heat it, as we did, we refluxed our reaction, this bond splits. And you probably remember why. This spontaneously produces nitrogen gas with the breakage of a weak bond, forming this radical. And the nitrogen gas bubbles off. Remember, this reaction is very dependent on the loss of gases, which drive all reactions forward. So these reactions should really go 100%. The way you control the amount of radical you have in the reaction is by controlling the amount of AIBN you have in the reaction. Okay, now, once you get your radical, this is all initiation, and you should have this in your notes. If you took good notes, you have this already. I probably shouldn't even be repeating this, but I am. So this reacts with the sulfuryl chloride. There are a lot of things the radicals can do. I talked about it in class. I'm not going to go into that now. Using fish hooks, because these are single electron processes, I'm going to make chlorinated tertiary nitrile, oops, lost my nitrile, and SO2 radical, SO2Cl radical. And as we said in class, this is another thing that will spontaneously produce a gas. So we got SO2 plus chlorine radical. Okay, now, once you did this, you finally have your chlorine radical. And the chlorine radical will attack this substrate. And what we said in class is there are 4 places it can attack, but I'm only going to focus on 2 of them right now. It can attack here, it can attack here, it can attack here, it can attack here, okay? In which case you'll get this radical, primary, old news, we don't care about that. This one, secondary of some interest. This one, secondary of some interest. And this one, primary of some interest. Plus HCl, HCl. Okay, there's another step. This is propagation 1. There are 2 other propagation steps. I'm not going to write them. Okay, but what your outcome depended on was the attack at this step. This is what determined the outcome. If you got most of that, it happened here. If you got most of that, it happened here. It happened at this step. So this is the only step we care about. Okay, now, as I told you, you want to focus on these 2. Okay, those 2. Why these 2? Because they're both secondary, and their only difference is the distance from the chlorine. We only want to have one variable in our experiment. Both secondary, their only difference is how far they are from the chlorine. We're also going to use this one as a comparison atom. Why? Because this primary is the closest to being a true primary of the primaries in the molecule. This primary is ridiculous. You do not want to consider this primary. It's too close to the chlorine. But this is the most likely to have not been affected by the chlorine, and it can be used for comparison. What's my time, Clem?
7 minutes about.
Okay, so I'm going to try to do a little bit with the data, and I'll probably follow this up later in the week with something else. Okay, but at the end of the lab, you got a GC. Okay? The GC looked like, probably like this. So you can go back and look at your GC. I encourage you to, like this. This is time. Okay? This is 1-chlorobutane. This is 1,1, 1,2, 1,3, and 1,4, all dichlorobutanes. Okay, do you remember how you controlled the reaction so you wouldn't get trichlorinated? We used a huge excess of 1-chlorobutane to increase the statistical likelihood that this would get hit and these would not get hit with chlorines. We went over that in class. Okay, you had data for these. I'm going to make up some data. I probably shouldn't do this. I'm going to get myself in trouble, no doubt. But let's say you had like 30% of this, 20% of that. I know I'm getting myself in trouble here. Let's make it higher. I'm going to make it 40%, 25%. Now I'm up to 65. 20 and 15. I don't know if this is going to work. All right. So say you got numbers like this. 20, 25, 40, 15. They're just numbers. These could be ridiculous numbers. They could have no meaning whatsoever. I don't know if you recall, but you had to take these numbers and you had to process them. Okay? You had to calculate the reactivity per hydrogen. So since the starting material had 2 hydrogens here, 2 here, 2 here, 2 here, and 3 here, this site was statistically favored. Even though it might not have been intrinsically favored, it was statistically favored. So you would have to take this number divided by 2, this number divided by 2, this divided by 2, and divide this by 3. The idea here is you want to get a reactivity per hydrogen. Not a reactivity for 3 hydrogens or 2 hydrogens, a reactivity per hydrogen. That would translate these numbers to 10, right, 12.5, 20, and 5. Okay? Then what you had to do was calculate a secondary to primary ratio. And I can already see that my ratios are going to be ridiculous. But you would take this number, exclude that number, take 12.5 and divide by 5, because this is for the number 2 position, and take 20 and divide by 5, and this is for the number 3 position. Now this is not very good data, because this is going to come out to be, what, 2.5? 2.5 to 1, and this is going to be 4 to 1. Oops, that's too high. Okay, now, how many more minutes do I have, Clem?
You're at almost 11.
11? Then I'm over time.
Oh, okay.
Okay, I can't even use it. All right, that's it. I can't use the movie.